Imagine sealing 10,000 people inside a machine and asking their descendants, hundreds of generations later, to step out onto an alien world none of them chose to reach. That is the promise of a generation ship. Build a vessel large enough to carry a population across the stars. Let them live, reproduce, and die on board until their distant children arrive. But the journey would last 10,000 years. Longer than recorded history. Longer than any nation, language, or religion has ever survived. The ship would need to recycle every molecule of air, water, and food without a single permanent failure for millennia. No machine humanity has ever built has lasted a fraction of that time. Today, we ask whether a generation ship could keep humans alive for 10,000 years. If you find these kinds of deep explorations fascinating, a quick like or subscribe really helps the channel grow. Now, settle in, get yourself comfortable, let's begin. The idea sounds almost simple. Build a ship large enough to hold a small city. Fill it with people, food, air, water, and everything needed to sustain human life. Point it toward another star. Let the passengers live, grow old, have children, and die on board, passing the mission forward generation after generation until their distant descendants finally arrive at the destination. It is one of the oldest dreams in science fiction and one of the most terrifying ideas in real engineering. Because the moment you sit down with a calculator and work through what the journey actually requires, the dream transforms into a problem so vast that it makes every other engineering challenge in human history look trivial. This is a generation ship, not a rocket that carries astronauts on a round trip, not a capsule designed to keep a crew alive for months or even years. A generation ship is a vessel built around a single devastating admission. The journey will take so long that no one alive at launch will survive to see the destination. Their children will not survive to see it. Their grandchildren will not survive to see it. Depending on the target star and the speed of the vessel, dozens or hundreds of complete human generations will be born, will live their entire lives, and will die inside the ship before it arrives. The mission does not depend on any individual human surviving. It depends on the unbroken chain of generations maintaining the vessel, the knowledge, and the purpose of the voyage across its full duration. The concept exists because of a single brutal fact about the universe. The stars are unimaginably far away. Proxima Centauri is the closest star to our solar system. It sits approximately 4.24 light-years from Earth. In astronomical terms, this is practically next door. Proxima Centauri is not on the far side of the galaxy. It is not hidden behind a nebula or buried in a distant star cluster. It is our nearest stellar neighbour, the closest sun to our own sun, and it is absurdly, heartbreakingly far away. 4.24 light-years translates to roughly 40 trillion kilometres. That number is so large it defeats human intuition entirely. To put it in terms that at least approach comprehension, consider this. The Moon sits about 384,000 kilometres from Earth. Humans crossed that distance in 3 days during the Apollo program. To reach Proxima Centauri, you would need to line up more than 100 million of those Earth-to-Moon trips end to end. The distance from the Earth to the Sun is about 150 million kilometres, one astronomical unit. Proxima Centauri is approximately 268,000 astronomical units away. Even light, the fastest thing in the universe, moving at roughly 300,000 kilometers per second, takes more than 4 years to make the crossing. Now consider how fast humanity can actually send a spacecraft. Voyager 1, launched in 1977, is currently the most distant human-made object from Earth. It travels at approximately 17 kilometers per second, or about 61,000 kilometers per hour. This is extraordinarily fast by human standards. A bullet from a high-powered rifle moves at roughly 1 kilometer per second. Voyager 1 moves 17 times faster than a bullet. It has been flying for nearly 5 decades and has traveled more than 24 billion kilometers from Earth. Yet at its current speed, Voyager 1 would require more than 70,000 years to cross the distance to Proxima Centauri if it were heading in that direction. 70,000 years. Anatomically, modern humans have existed for roughly 300,000 years. The entire history of agriculture, cities, writing, empires, science, industry, and spaceflight fits inside the last 10,000. Voyager 1 would need 7 times that span just to reach the nearest star. Even dramatically faster spacecraft face crushing timescales. Suppose engineers manage to build a vessel capable of traveling at 1% of the speed of light. That is approximately 3,000 kilometers per second, nearly 200 times faster than Voyager 1. Such a speed would represent an engineering achievement far beyond anything currently achievable, requiring energy sources and propulsion systems that exist today only as theoretical concepts. At 1% of light speed, the journey to Proxima Centauri would still take approximately 424 years, more than 4 centuries, longer than the entire history of the United States, longer than the gap between the Renaissance and the modern era, and Proxima Centauri is the closest star. A target 10 light-years away would require 1,000 years at that speed. A target 50 light-years away, which opens up a much wider selection of potentially habitable worlds, would demand 5,000 years in transit. Push the speed higher. 5% of the speed of light, a figure sometimes discussed in connection with highly theoretical nuclear pulse propulsion concepts, would shorten the trip to Proxima Centauri to roughly 85 years. That begins to approach a single human lifespan. But even this extraordinary speed helps only for the nearest stars. A target 20 light-years away still demands 400 years at 5% of light speed. A target 50 light-years away demands 1,000. And 5% of light speed is not something any real spacecraft has ever come close to achieving. The energy required to accelerate a vessel massive enough to carry a human population, along with all its life support equipment, radiation shielding, food production systems, structural mass, and the fuel for deceleration at the other end, to even 1% of light speed is staggering. The fuel requirements scale exponentially with velocity. Every additional fraction of a percent demands enormously more energy. A craft that can reach 5% of light speed while carrying thousands of people and their entire self-sustaining habitat would require energy budgets that challenge the total output of current human civilization. This is why the generation ship exists as a concept. It is not a first choice. Nobody looks at the stars and says, "I want to spend 10,000 years getting there." The generation ship is the answer to a question that nobody wanted to ask. If we cannot make the journey fast enough for a single crew to survive it, then we must build a vessel where the crew is continuously replaced. Not through crew rotations or shift changes, but through the biological process of reproduction. The ship carries a breeding population. Children are born during the voyage, raised inside the vessel, educated in its systems, trained in its operations, and they grow old and die without ever setting foot outside the hull. Their children repeat the cycle, and the cycle continues, generation after generation, for as long as the journey takes. The mission does not end if any individual dies. It ends only if the population dies, or if the knowledge required to operate the ship is lost, or if the ship itself fails beyond repair. At 1% of light speed, a journey to a star 10 light-years away takes 1,000 years. That is roughly 40 human generations. A star 50 light-years away demands 5,000 years, or 200 generations. And if the achievable speed is lower than 1% of light speed, which is entirely possible given current engineering limitations, the numbers climb further. A journey at 1/10 of 1% of light speed, still vastly faster than any spacecraft currently in existence, would require more than 40,000 years to reach a star 40 light-years away. The range of plausible travel times for a generation ship extends from centuries at the optimistic end to tens of thousands of years at the pessimistic end. The specific number depends on the propulsion technology, the target distance, and the total mass of the vessel. 10,000 years sits somewhere in the middle of this range. It is not the longest possible journey. It is not the shortest. But it is the number that fundamentally changes the nature of the problem. Because 10,000 years is not merely a long time. It is a duration that transforms the entire premise of what the ship is and what it must do. A journey of a few hundred years is difficult, but conceptually manageable. The crew that launches the mission might personally know the children who know the grandchildren who arrive. Cultural continuity across 10 or 15 generations is challenging, but historically precedented. Dynasties have lasted that long. Religious orders have persisted for centuries. Languages evolve over such timescales but remain mutually intelligible. The ship's original engineers could leave behind maintenance manuals, training programs, and institutional knowledge that the arriving generation can still read and understand. A 300-year mission is a long voyage, but it is still recognizably a voyage, a trip with a beginning, a middle, and an end that the passengers can conceptually grasp within the context of their own cultural memory. 10,000 years is not a long voyage. It is a different category of existence entirely. Consider what the world looked like 10,000 years ago. Human beings were just beginning to domesticate wheat and barley in the Fertile Crescent. The first permanent settlements were appearing in places like Jericho. The Seaman times, writing did not exist and would not be invented for another 5,000 years. The wheel had not been conceived. Metalworking was unknown. No building standing today was standing then. No city that exists today existed in its current form then. No language spoken anywhere on Earth today was spoken in any recognizable form 10,000 years ago. English did not exist. Latin did not exist. Sanskrit did not exist. The linguistic ancestors of every modern language were themselves so different from their modern descendants that no living speaker would understand a single word. No government has survived 10,000 years. No religion currently practiced has roots that stretch back that far in any continuous, unbroken form. The Catholic Church, one of the longest-lived institutions in human history, is roughly 2,000 years old. The oldest continuously inhabited cities, places like Damascus and Aleppo, trace their habitation back roughly 10 or 11,000 years. But the cultures within them have been replaced, conquered, transformed, and rebuilt so many times that nothing connects the modern inhabitants to the original settlers except the location itself. 10,000 years is longer than the entire span of recorded human history. Every empire that has risen and fallen, every language that has been spoken and forgotten, every religion that has been founded, spread, and either survived or vanished, all of it fits within the last 5,000 or 6,000 years. 10,000 years contains all of this and reaches back further still, into a world so alien to modern experience that we can reconstruct it only through archaeology and educated guessing. A generation ship attempting to cross 10,000 years would not be undertaking a long trip. It would be attempting something no human society has ever accomplished under any conditions, including the most favourable conditions imaginable. It would be asking a sealed community, locked inside a metal shell with no external resources, no rescue capability, and no margin for permanent failure, to maintain perfect continuity of knowledge, technology, social order, biological health, and mechanical function for longer than the combined lifespans of ancient Egypt, the Roman Empire, the Byzantine Empire, the Ottoman Empire, and every modern nation-state laid end to end. On a planet with unlimited resources, open skies, natural weather, wild genetic diversity, and an entire biosphere working around the clock to keep its inhabitants alive, no civilization has managed this. The generation ship must accomplish it inside a can. This timescale forces a fundamental transformation in what the ship actually is. At the moment of launch, it is a spacecraft, a vehicle with a crew, a destination, and a mission plan. The people on board know why they are there. They remember Earth. They understand the stars. They can read the mission documents and comprehend the engineering schematics. But within a few generations, the people on board will have no living memory of Earth. No one alive will have met anyone who stood on a planetary surface. Within a few more generations, Earth will become a story told by elders, then a chapter in a history text, then a set of images in an archive that fewer and fewer people bother to access. The destination, too, will be abstract, not a real place with sunlight and wind and soil, but a dot on a navigation display. A concept inherited from ancestors who are becoming increasingly mythological. The only world the passengers know, the only world they have ever experienced with their own senses, is the ship itself. And this is the moment the ship stops being a vehicle and becomes a world. Consider what Earth provides for its inhabitants without any conscious effort on their part. The planet generates a magnetic field powered by convection currents in its molten iron core, deflecting the most dangerous charged particles streaming from the sun and from deep space. It holds an atmosphere containing roughly 78% nitrogen, 21% oxygen, and a balance of trace gases that supports human respiration. It cycles water through evaporation from oceans, condensation into clouds, precipitation as rain, filtration through soil, and collection in rivers and aquifers, distributing fresh water across 510 million square kilometers of surface area. It grows food through ecosystems involving billions of species of plants, animals, fungi, bacteria, and other microorganisms, each playing roles in nutrient cycling, pollination, decomposition, soil formation, and pest control. It maintains a temperature range compatible with liquid water through a greenhouse effect balanced across geological timescales. It provides gravity at a steady 9.8 meters per second squared through sheer planetary mass. And perhaps most importantly, it buffers against catastrophe through scale. If a forest burns, other forests remain. If a crop fails, other crops grow elsewhere. If a river dries up, other rivers flow. If a disease devastates one population, genetic diversity in other populations provides resistance. Earth's resilience comes not from any single system, but from the staggering redundancy of operating across an entire planet. A generation ship must replicate every one of these functions inside a sealed container, using only the materials and energy sources it carries at launch or can manufacture internally, not approximately, not partially. Completely. Because in deep interstellar space, there is no backup. There is no second planet waiting nearby. There is no resupply mission that can reach the ship. There is no emergency evacuation route. Every molecule of breathable air, every liter of drinkable water, every calorie of food, every watt of power, every replacement component for every critical system must come from within the hull. And it must keep coming, without interruption, for 10,000 years. The atmosphere inside the ship must be manufactured, filtered, chemically balanced, and recycled continuously. Carbon dioxide exhaled by thousands of people must be captured and converted back into breathable oxygen through either chemical processes or biological systems involving plants and microorganisms. Toxic trace gases produced by human metabolism, by industrial processes, by chemical reactions in materials, by biological decay, must be detected and removed before they accumulate to dangerous concentrations. The nitrogen-oxygen balance must be maintained within narrow tolerances. Humidity must be controlled to prevent both dehydration and fungal growth. A single sustained failure in atmospheric management does not produce discomfort. It produces suffocation, poisoning, or both. Water must be recycled with near-perfect efficiency. Every drop of perspiration, every exhaled breath containing water vapor, every liter of urine, every rinse of every surface must be captured, purified, and return to the supply. On Earth, the hydrological cycle operates across an entire planet, with oceans containing approximately 1.3 billion cubic kilometers of water, providing virtually infinite buffering capacity. Inside the ship, the total water supply is fixed at launch. Lose even a small fraction of a percent per year to leakage, to chemical reactions that bind water molecules into non-recoverable compounds, or to incomplete purification, and over centuries the reserves steadily decline. Over 10,000 years, even a cumulative loss rate that would be considered negligible in any terrestrial system becomes fatal. Food production demands an even more staggering level of self-sufficiency. The ship must grow all of its own food using artificial lighting, recycled nutrients, and carefully controlled agricultural environments. This is not a greenhouse. This is not a garden. This is the entire agricultural output of a small nation, operating without natural sunlight, without soil replenished by geological weathering, without pollination by wild insect populations that evolved alongside the crops over millions of years, without the deep genetic reservoirs of wild plant relatives that allow breeders to develop disease-resistant varieties, and without the vast microbial ecosystems that make terrestrial soil fertile. Every calorie consumed by every person on board for 10,000 years must be grown, harvested, processed, and distributed using systems that function without permanent interruption. Waste recycling closes the loop. Human biological waste, food scraps, dead plant material, worn-out clothing, broken equipment, chemical byproducts, all of it must be decomposed, processed, and converted back into usable raw materials. On Earth, this is handled by trillions upon trillions of microorganisms operating in soil, water, and sediment across the entire planetary surface, recycling nutrients through biogeochemical cycles that took billions of years to evolve and stabilize. On a ship, decomposition and nutrient recovery must be engineered, monitored, and controlled artificially. If the waste processing system degrades or fails, the ship does not merely become unpleasant. Toxic compounds accumulate. Nutrients become chemically locked in unusable forms. The agricultural system loses its input stream. The food supply collapses. The population starves. And then there is radiation. In deep interstellar space, far beyond the protective magnetic field of any star, the ship is continuously bombarded by galactic cosmic rays. These are high-energy particles, primarily protons and heavier atomic nuclei, accelerated to near light speed by supernova explosions and other violent astrophysical processes across the galaxy. They strike with energies that penetrate meters of conventional shielding material and damage living tissue at the molecular level. They break DNA strands. They ionize atoms within cells. They create secondary radiation showers as they interact with the ship's hull. On Earth, the planet's magnetic field and thick atmosphere absorb or deflect the vast majority of galactic cosmic radiation. A generation ship has neither. It must carry its own shielding, whether in the form of massive physical barriers, electromagnetic field generators, or water and hydrogen-rich materials packed into the hull. And the shielding must function without degradation for the entire journey, because the damage from cosmic radiation is cumulative. It does not announce itself with alarms or dramatic symptoms. It accumulates silently, year after year, manifesting as elevated cancer rates, cognitive impairment, and cellular damage that compounds across every generation exposed to it. The biological consequences of this exposure inside a closed population are devastating, and we will return to them. Artificial gravity adds another structural demand. Human physiology depends on gravitational loading. Without it, bones lose mineral density, muscles atrophy, cardiovascular systems weaken, cerebrospinal fluid redistributes in ways that damage optic nerves and impair vision, and immune function deteriorates. Astronauts aboard the International Space Station show measurable physiological degradation within months of arriving in microgravity, despite rigorous daily exercise regimens. A generation ship population living without gravity for thousands of years would become biologically incapable of functioning on a planetary surface, which would render the entire mission pointless. The standard theoretical solution is rotation. Spin the habitat section of the vessel to generate centrifugal force that mimics gravitational pull. This is physically sound, but structurally enormous. To produce Earth-equivalent gravity without inducing severe Coriolis effects that cause nausea and disorientation, the rotating section must have a radius of several hundred meters at minimum. Building a rotating structure this large, capable of withstanding continuous centripetal stress for 10,000 years without developing fatigue cracks, weld failures, or bearing degradation, is a problem no engineer has ever faced. Power sustains all of it. The lights that illuminate the farms, the fans that circulate the atmosphere, the pumps that move water through recycling systems, the heaters and coolers that regulate temperature, the computers that monitor every sensor, the manufacturing equipment that produces replacement components. Every function aboard the ship requires energy. In interstellar space, far from any star, solar panels produce nothing. Chemical fuels would be consumed within a few years at best. The only plausible power source for a journey of this duration is nuclear, either fission reactors burning carefully rationed fuel, or fusion reactors if that technology can be made practical. Even nuclear systems are not eternal. Reactor components degrade under their own neutron bombardment. Fuel elements must be reprocessed or replaced. Control systems require maintenance. A generation ship must either carry enough nuclear fuel for 10,000 years of continuous power generation, or develop the capacity to manufacture or breed new fuel on board. And heat, the problem nobody thinks about, governs the ship's survival as surely as air or water. Every biological process generates waste heat. Every machine generates waste heat. Every watt of electrical power eventually becomes thermal energy that must be expelled from the vessel. In the vacuum of space, there is no air to carry heat away. There is no ocean to absorb it. The only mechanism for shedding heat is thermal radiation, emitting infrared energy from large radiator surfaces into the void. These radiators must be enormous. They must face open space, and they must function without clogging, corroding, or losing efficiency for the entire journey. If thermal management fails, the interior temperature of the ship rises steadily. Electronics overheat and malfunction. Biological systems collapse. The ship cooks itself from within, and there is nowhere for the heat to go. Each of these systems, atmosphere, water, food, waste, radiation protection, gravity, power, and thermal management, represents an individual engineering challenge of extraordinary difficulty. But the true horror of the generation ship problem is that none of them operates in isolation. They are all coupled, all interdependent, all feeding into and depending upon one another in a web of mutual reliance that mirrors the interconnected biogeochemical cycles of a living planet. The food system needs light from the power system, water from the recycling system, and nutrients from the waste system. The waste system needs energy to operate its processes. The power system generates heat that must be managed by the thermal system. The atmospheric system depends on the food system's plants for oxygen regeneration. The water system feeds the food system, which feeds the people, who produce the waste, which feeds the recycling system, which feeds the food system again. A failure in any one system cascades into every other system. The ship is not a collection of independent machines bolted together. It is a single interdependent organism, and like any organism, it can die from the failure of a single critical organ. No machine humans have ever built has operated without maintenance or component replacement for more than a few decades. The International Space Station, the most sophisticated closed habitat ever operated in space, requires continuous resupply from Earth, regular crew intervention to repair malfunctioning components, and periodic replacement of entire modules. It was designed for a 15-year service life, later extended to 30. The Voyager probes have operated for nearly 50 years, but they are simple instruments with no moving biological systems, no recycling requirements, and no passengers. Complex technological systems on Earth, power plants, water treatment facilities, transportation networks, all require constant human maintenance, regular overhaul, and eventual complete replacement of worn components. They last decades under the best circumstances. A generation ship must last more than 300 times longer than the International Space Station's extended service life. And it must do so while simultaneously supporting a living population, growing food, recycling waste, shielding against radiation, generating power, and maintaining structural integrity under continuous rotational stress. The generation ship is not a big spaceship with families on board. It is not an ocean liner pointed at the stars. It is an attempt to construct an entirely self-sustaining artificial world, a world that must function with the mechanical precision of a spacecraft and the ecological resilience of a planet for a duration longer than any civilization in human history has managed to survive on the surface of Earth itself. And the engineering nightmare, as immense as it is, represents only half the problem. Because even if every machine on board functions flawlessly for the entire journey, the ship still carries the most unpredictable, fragile, and failure-prone system ever devised. It carries a human civilization, thousands of people living, aging, reproducing, disagreeing, forgetting, and changing across 400 generations of unbroken confinement. The machines must survive 10,000 years, but so must the knowledge of how to operate them. So must the social structures that organize the labor. So must the educational systems that train each new generation. So must the governance that prevents conflict from escalating into destruction. So must the collective memory of why the ship is flying in the first place. What comes next reveals why the ship's deadliest enemy is not the vacuum outside the hull, but the slow accumulation of tiny failures within it. Failures in metal, in seals, in circuits, in bearings, and in every physical component that must somehow last longer than anything humans have ever built. Everything described so far sounds overwhelming in principle. The air recycling, the water purification, the food production, the waste processing, the radiation shielding, the power generation, the thermal management, but the natural response to such a list is optimism. Surely, given enough time and enough engineering, humanity could solve these problems. We split the atom, we landed on the moon, we built a space station that has been continuously occupied for more than 2 decades. Given centuries of further development, could we not build a ship capable of sustaining life indefinitely? The answer depends entirely on how honestly we examine the evidence. And the evidence, drawn from every closed life support experiment and every long-duration space mission ever conducted, tells a consistent and sobering story. Humanity has never successfully operated a fully closed life support system for any meaningful duration. Not for 10,000 years, not for 1,000, not for 100, not even for 2. Start with the best system currently operating in space. The International Space Station maintains human life through a network of hardware collectively known as the Environmental Control and Life Support System. This system represents decades of NASA and international engineering. It filters the atmosphere, removing carbon dioxide and trace contaminants. It generates oxygen through electrolysis, using electrical current from the station's solar panels to split water molecules into hydrogen and oxygen gas. It recycles water recovered from crew perspiration, exhaled moisture, and urine through a series of filtration, distillation, and purification steps. Current estimates place the station's water recovery rate at approximately 90 to 98%, depending on which subsystems are operating and how efficiency is measured. This is a genuine engineering achievement. It dramatically reduces the amount of water that must be launched from Earth, saving enormous costs and mass. But it is not a closed system. Not even close. Every cargo ship that docks with the station carries water to replace the fraction lost through incomplete recycling. It carries food because the station grows essentially none of its own. It carries replacement filters, catalysts, and chemical reagents consumed by the life support hardware. It carries spare parts for pumps, fans, sensors, valves, and control units that wear out or malfunction. The station's atmosphere loses small quantities of gas through microleaks and through airlock operations, and these must be replenished. The environmental control and life support system was never designed to operate without resupply. It was designed to reduce resupply, which is a profoundly different engineering objective. Reducing the mass launch from Earth saves money. Eliminating resupply entirely saves lives, because on a generation ship there is no Earth to launch from. The gap between 98% water recovery and 100% water recovery may sound small, 2%, almost nothing. But aboard a vessel that carries a fixed water supply at launch and cannot replenish it from any external source for 10,000 years, that 2% is the difference between survival and slow dehydration. 2% loss per year means the total water supply halves in roughly 35 years. Even 2% per decade would drain the reserves within a few centuries. A generation ship requires not 98% recycling but something indistinguishable from 100%, sustained across every subsystem, for the entire journey. No margin, no resupply, no second chance. And humanity has not yet demonstrated that level of closure in any system, anywhere, for any length of time. The most ambitious attempt to build a closed ecological system on Earth ended in a lesson so stark that its implications still haunt life support engineers. Biosphere 2 was constructed in the Arizona desert in the late 1980s. It enclosed approximately 1.3 hectares under glass and steel, creating an airtight facility containing multiple simulated biomes, including rainforest, ocean, savanna, marsh, and desert, along with an agricultural area designed to grow food for a crew of 8 people. The structure was sealed in September of 1991, with its crew inside. The plan was to demonstrate that a closed ecosystem could sustain human life for 2 years without material exchange with the outside world. Energy from sunlight was permitted. No air, water, or food would enter or leave. The experiment began failing almost immediately, though the full scale of the failure took months to become apparent. Oxygen levels inside the structure began declining steadily. Carbon dioxide levels rose. Microbes in the excessively rich soil consumed oxygen at rates the designers had not anticipated, and the concrete structural elements of the facility absorbed carbon dioxide through chemical reactions, locking it away in a form the plants could not access. Within 16 months, oxygen concentration had dropped from the normal atmospheric level of roughly 21% to approximately 14%, equivalent to conditions at an altitude of more than 4,000 meters. The crew experienced chronic fatigue, impaired cognitive function, and difficulty performing physical tasks. Supplemental oxygen had to be pumped in from outside, breaking the closure and invalidating the fundamental premise of the experiment. But the atmospheric crisis was only one dimension of the failure. The agricultural system could not produce enough food to sustain 8 people. Crops grew poorly under the filtered light of the glass enclosure, which blocked certain wavelengths needed for optimal photosynthesis. Pest species thrived in the sealed environment, while many pollinating insects died off, including most bee populations. Cockroaches and a particular species of ant proliferated explosively in the absence of natural predators, competing with the crew for food. Morning glory vines invaded the agricultural plots and proved nearly impossible to control. The crew lost weight steadily and experienced chronic hunger throughout much of the mission. The ecosystem itself proved far less stable than its designers had predicted. Species went extinct inside the enclosure at alarming rates. 19 of 25 vertebrate species introduced into Biosphere 2 died out. Most pollinating insects vanished. The carefully designed ecological communities simplified and destabilized, with a few aggressive generalist species dominating while specialized organisms disappeared. The ocean biome required chemical intervention to maintain pH levels as carbon dioxide dissolved into the water and formed carbonic acid. The coral reef began dying within months, and the social dynamics fractured under pressure. 8 people living in a sealed enclosure under conditions of chronic hunger, oxygen deprivation, and mounting evidence that their life support system was failing, split into 2 opposing factions that essentially stopped communicating with each other. Interpersonal conflict became severe enough to impair cooperation on tasks critical to the experiment's survival. The second mission, conducted in 1994 with a different crew, ended prematurely amid management disputes and allegations that the closure protocols had been violated. Biosphere 2 was not a small experiment. It was a massive, expensive, carefully engineered facility built on the surface of Earth, where gravity was free, sunlight was abundant, structural integrity was guaranteed by a firm foundation, and the ambient environment outside the glass was breathable air at normal pressure and temperature. If 8 people could not maintain a closed ecosystem under these ideal conditions for 2 years, the implications for a sealed vessel carrying thousands of people through deep space for millennia are devastating. The failure did not result from a single engineering error. It resulted from the fundamental complexity of closed ecological systems. Every organism within the enclosure interacted with every other organism and with the physical environment in ways that could not be fully predicted or controlled. Small imbalances cascaded into systemic instability. The lesson was not that the designers were incompetent. The lesson was that Earth's biosphere maintains its stability through scale, redundancy, and diversity so vast that no artificial enclosure can replicate it. More than 3 decades later, the most advanced bioregenerative life support research in the world has still not overcome these fundamental challenges. The European Space Agency has been developing the Melissa project, the microecological life support system alternative, since 1989. Melissa is designed as a loop of interconnected bioreactors using bacteria, cyanobacteria, and higher plants to recycle human waste into clean water, breathable air, and edible food. The system is elegant in concept, dividing the recycling process into specialized compartments that mirror the functional roles of different ecological communities on Earth. Thermophilic bacteria break down solid waste. Nitrifying bacteria convert ammonia into nitrates that plants can absorb. Photosynthetic organisms, including the edible Cyanobacterium Limnospira indica, produce oxygen and serve as a supplemental food source. Higher plants provide additional food and atmospheric processing. After more than 35 years of development across a consortium of 15 partner institutions, the Melissa pilot plant in Barcelona is only now preparing its first experimental closure tests involving 4 compartments operating together in continuous mode. The system has never supported a human crew. It has never operated in space. As of the most recent reports, the project is working through integration and characterization of the compartment connections, with full loop closure still an aspirational goal rather than a demonstrated reality. This is not a criticism of the scientists and engineers involved. It is evidence of how extraordinarily difficult closed-loop life support is. 35 years of focused international research have brought us to the point of tentatively connecting 4 biological compartments in a ground-based pilot facility. Scaling this to support thousands of people aboard a spacecraft and keeping it operating reliably for 10,000 years represents a leap so enormous that no credible researcher claims it is achievable with current or near-future technology. Meanwhile, the radiation problem compounds every biological challenge. In deep interstellar space, beyond the protective magnetosphere of any star, the ship's population is exposed to a continuous flux of galactic cosmic rays. These are not the relatively mild solar radiation that astronauts experience in low Earth orbit. where the planet's magnetic field still provides substantial shielding. Galactic cosmic rays include heavy ions, the nuclei of elements like iron and carbon, accelerated to enormous energies by astrophysical processes. These particles carry so much energy that they penetrate deep into shielding material, and when they strike atomic nuclei in the hull, they produce cascades of secondary particles that can be even more damaging than the primary radiation. No practical thickness of aluminum, steel, or even water fully stops galactic cosmic rays. The most effective shielding materials are hydrogen-rich substances like polyethylene and water, but even meters of such material merely reduce the dose rather than eliminating it. NASA currently limits astronaut career radiation exposure to 600 millisieverts. On the International Space Station, astronauts receive roughly 200 to 300 millisieverts per year depending on solar conditions, while still partially protected by Earth's magnetosphere. In deep space beyond that protection, the annual dose from galactic cosmic rays alone is estimated at roughly 300 to 400 millisieverts, with minimal shielding. Over a single human lifetime of 70 years, this produces cumulative doses well above what terrestrial radiation safety standards would permit. Over 10,000 years, every generation absorbs this dose. The health consequences extend beyond the individuals exposed, reaching into the population's genetic future in ways that will be examined in detail shortly. But the engineering problem is immediate and severe on its own terms. Every proposed shielding material degrades under the very radiation it is designed to stop. Polyethylene becomes brittle. Water shielding systems require continuous pumping and containment that are themselves subject to mechanical failure. Electromagnetic shielding concepts demand enormous sustained power expenditure. The shielding is not a passive barrier installed at launch and forgotten. It is an active system requiring maintenance, monitoring, and eventual replacement, adding yet another link to the chain of systems that must never break. Shielding reduces the problem, it does not solve it. And the shielding itself, whatever form it takes, must maintain its integrity for the full duration of the mission, because cosmic ray bombardment degrades the very materials designed to stop it. This brings us to the deepest and most inescapable engineering challenge of a 10,000-year mission. Everything breaks. Not eventually, not hypothetically. With mathematical certainty, every material known to science degrades over time. Metals fatigue. Crystalline structures shift under cyclic stress. Welds develop microcracks. Bearings wear. Seals harden, shrink, and leak. Polymers exposed to radiation become brittle and fragment. Lubricants oxidize and lose viscosity. Electronic components drift out of specification as charge carriers migrate through semiconductor junctions. Solder joints develop whiskers, tiny metallic filaments that grow spontaneously from tin-based solders and can short-circuit adjacent conductors. Corrosion attacks metal surfaces even in controlled atmospheres, because perfectly inert environments are impossible to maintain in a vessel containing water, biological organisms, and active chemical processes. The International Space Station demonstrates this reality on a timescale of decades. Astronauts spend a significant fraction of their working hours on maintenance. They replace failed fans, repair water recycling equipment, patch ammonia coolant leaks, swap out degraded battery modules, and troubleshoot electronic malfunctions. The station requires continuous intervention by trained crew members backed by teams of engineers on Earth who can diagnose problems remotely and develop repair procedures. Even with this level of support, critical systems fail regularly enough that redundancy and spares are essential design features. Every major system has backup units. Every backup unit has a replacement scheduled for delivery from Earth. A generation ship cannot receive replacement parts from Earth. It cannot call mission control for troubleshooting advice. And it cannot rely on redundancy alone to survive 10,000 years, because redundant systems also degrade. A backup pump does not help if both the primary and backup pumps have exceeded their material lifespan. Triple redundancy does not help if all three units fail within the same century. Redundancy buys time, it does not buy eternity. Consider bearings. Simple mechanical bearings, the components that allow rotating shafts to turn smoothly, are among the most common failure points in any mechanical system. The ship's rotational gravity system depends on bearings or equivalent mechanical interfaces that must handle continuous loads for the entire journey. Bearing failure modes include surface fatigue, where microscopic cracks form on the contact surfaces and propagate until pieces spool off. Lubrication breakdown, where the grease or oil that reduces friction degrades chemically or is squeezed out of the contact zone. Contamination, where particles from worn components enter the bearing and accelerate abrasion. Even the highest quality bearings manufactured on Earth have rated lifespans measured in years or decades under continuous operation, not millennia. Consider seals. The ship's atmospheric containment depends on thousands of seals at every joint, hatch, viewport, pipe connection, and mechanical penetration through the pressure hull. Elastomeric seals, the rubber-like materials used in most sealing applications, degrade through oxidation, radiation exposure, compression set, and chemical attack from the substances they are designed to contain. Even the most durable elastomers lose flexibility and sealing effectiveness within decades. Metal seals last longer but are less forgiving of thermal expansion, vibration, and manufacturing imperfections. A single failed seal in a critical atmospheric boundary can depressurize a compartment. Across 10,000 years of continuous service, the total number of seal years accumulated by all seals aboard the ship is astronomical. Even a fantastically low failure rate per seal per year produces a near certainty of multiple failures when multiplied across enough seals and enough time. Consider electronics. Modern civilization depends on semiconductor devices that were not designed for millennia of service. Transistors degrade through hot carrier injection, electromigration, oxide breakdown, and radiation-induced charge trapping. Memory devices lose data retention over years. Processors slow down as their internal structures shift at the atomic level. An individual microchip might last 30 or 50 years in a benign environment. In a radiation-saturated deep space environment, degradation accelerates dramatically. The ship's computers must control atmospheric composition, monitor reactor performance, regulate temperature, manage agricultural lighting schedules, track navigation, and coordinate thousands of other functions. When they fail, they must be replaced. When the replacements fail, new ones must be manufactured on board, and the manufacturing equipment itself is subject to the same degradation. This is the insight that transforms the generation ship from an engineering challenge into an almost philosophical impossibility. The ship cannot simply be built well enough to last 10,000 years, because no material and no machine lasts that long. Instead, the ship must carry the capacity to rebuild itself, not once, not occasionally, continuously. Every component that wears out must be manufactured anew from raw materials carried on board. Every circuit board, every bearing, every seal, every pipe, every structural beam, every bolt, every sensor, every medical instrument, every agricultural lamp, every pump impeller, every heat exchanger surface, every square meter of radiation shielding that degrades under bombardment. The ship is not a machine. It is a factory that produces machines, including replacement parts for itself. This requirement cascades into staggering complexity. Manufacturing replacement bearings requires machine tools, lathes, grinders, heat treatment furnaces, and quality inspection instruments. Manufacturing replacement electronics requires semiconductor fabrication equipment, clean rooms, photolithographic systems, chemical etching baths, and testing apparatus. Manufacturing replacement seals requires polymer synthesis capability, vulcanization equipment, and precision molding tools. Each of these manufacturing systems is itself made of components that degrade and must eventually be replaced. The ship must manufacture the machines that manufacture the parts that keep the ship running, and it must manufacture the machines that manufacture the machines. The regression does not stop until you reach raw materials. What raw materials does the ship carry? Metals must be refined, alloyed, cast, forged, and machined. Where do the ores come from aboard a sealed vessel? They come from recycled components, from worn-out parts that are melted down and reforged. The ship must operate a complete metallurgical cycle, smelting, refining, alloying, and casting metals from its own aging infrastructure. Polymers must be synthesized from chemical feedstocks. Where do those feedstocks come from? From the decomposition of old polymers, from biological waste streams, from carefully managed chemical reserves. The ship must run a chemical industry. Semiconductors require ultra-pure silicon, rare dopant elements, and exotic materials for specialized applications. These must be recovered, purified, and reprocessed from expired electronics. The ship must operate a recycling infrastructure as sophisticated as a small industrial nation. To grasp what this industrial requirement actually means in practice, follow a single failure through the full chain of recovery. A coolant pump in one of the ship's fission reactors develops a crack in its impeller housing. The impeller is a precision-machined component that spins at thousands of revolutions per minute, forcing liquid coolant through the reactor's heat exchange loop. Without it, the reactor cannot shed heat efficiently. If the pump is not replaced, the reactor must be throttled back or shut down entirely, reducing the ship's total power output and forcing rationing of electricity across every system that depends on it. Replacing the impeller requires a new casting. The casting requires a specific alloy of steel with precise proportions of chromium, nickel, and molybdenum to resist corrosion and fatigue at the temperatures and pressures inside a reactor coolant loop. These elements do not exist aboard the ship in pure stockpiles waiting to be used. They exist locked inside the old impeller, inside other aging components elsewhere on the ship, and inside the metallurgical waste stream from previous recycling operations. The old impeller must be removed, cleaned, and transported to the ship's foundry. There it must be melted down, its constituent elements separated through chemical or electrochemical refining processes, each element purified to the grade required for the new alloy. The purified elements must be combined in exact proportions, melted again, and cast into a blank roughly matching the shape of the finished impeller. The blank must then be machined. This requires a lathe capable of holding tolerances measured in thousandths of a millimeter, cutting tools made from materials harder than the alloy being shaped, and a machinist trained not just to operate the equipment, but to understand why the tolerances matter and what happens if they are not met. After machining, the impeller must be heat-treated to achieve the correct crystalline grain structure, because an impeller with the wrong microstructure will fatigue and crack far sooner than one properly treated. After heat treatment, it must be balanced, because an impeller that wobbles even slightly at operating speed will destroy its bearings within months. After balancing, it must be inspected, using techniques that can detect subsurface flaws invisible to the eye, because a hidden crack in a reactor coolant pump is not a minor defect. It is a countdown to the next failure. The entire process, from failure detection to reinstallation of a functioning replacement, requires metallurgists, chemists, foundry operators, machinists, heat treatment specialists, quality inspectors, and reactor technicians, each trained to a standard that would be considered professional grade in any terrestrial industrial economy. It requires functioning equipment at every stage of the chain, and it requires that none of the equipment used in the process has itself degraded beyond operational limits, because if the lathe cannot hold tolerance, or if the furnace cannot reach temperature, or if the inspection instruments have drifted out of calibration, the replacement impeller will be defective, and the entire chain must begin again with even fewer resources and even less time. This is one component, one pump, one reactor. The ship contains thousands of components of comparable complexity, each on its own degradation timeline, each requiring its own chain of recovery when it fails. And every one of these industrial processes requires energy, generates waste heat, produces chemical byproducts that must be managed, and creates demands on the atmospheric and water recycling systems. The manufacturing sector of the ship is not separate from the life support sector. It is entangled with it. Running a smelter consumes power and generates fumes that must be filtered from the air the crew breathes. Operating a chemical synthesis plant produces waste streams that must be processed without contaminating the water supply. Semiconductor fabrication requires ultra-clean environments maintained by filtration systems that themselves consume energy and produce waste. The industrial metabolism of the ship and the biological metabolism of the crew share the same closed resource pool. Every atom used for manufacturing is an atom not available for food production, water recycling, or atmospheric processing. The ship's engineers must balance industrial output against biological needs across centuries, making trade-offs that accumulate in consequences over generations. The maintenance problem also requires knowledge. Every generation aboard the ship must understand not only how to operate the current systems, but how to diagnose failures, identify root causes, design replacement components, operate manufacturing equipment, and perform quality assurance testing on the products. This is not a matter of following instruction manuals. Complex system maintenance requires deep understanding of the underlying physics, chemistry, materials, science, and engineering principles. A crew that can replace a pump but does not understand fluid dynamics cannot redesign the pump when the original design proves inadequate after 3,000 years of operational feedback. A crew that can swap a circuit board but does not understand semiconductor physics cannot fabricate a new one when the last spare is consumed. The ship, therefore, must maintain not just a maintenance crew but an engineering civilization. It must operate schools that teach physics, chemistry, metallurgy, biology, medicine, electronics, computer science, agriculture, and every other discipline required to understand and sustain the systems aboard. It must preserve and transmit this knowledge perfectly across hundreds of generations, adapting the curriculum as systems evolve and new problems emerge, without ever losing the foundational understanding that makes adaptation possible. A gap of even a single generation, a period where the educational system falters and produces a cohort that does not fully understand the ship's systems, could create a cascade of deferred maintenance, misdiagnosed failures, and improvised repairs that degrades the vessel's functionality in ways that become increasingly difficult to reverse. Nuclear power systems illustrate the convergence of all these challenges. Whether the ship uses fission or fusion reactors, the power system must operate continuously for 10,000 years. No nuclear reactor on Earth has operated for more than approximately 60 years, and even that lifespan requires extensive maintenance, component replacement, and periodic major overhauls. Reactor vessels become brittle under continuous neutron bombardment. Fuel assemblies must be reprocessed or replaced. Control mechanisms must be recalibrated. Coolant systems develop leaks. Instrumentation drifts. Heat exchangers foul. A generation ship must either carry dozens of complete reactor systems to be used sequentially as each one reaches the end of its service life, or it must carry the full industrial capability to manufacture reactor components, reprocess nuclear fuel, and build new reactors from processed materials. Either approach requires staggering mass, complexity, and an unbroken chain of expertise spanning the entire journey. The scale of industrial capacity required leads to a paradox. The ship must be large enough to carry all of this manufacturing infrastructure, which increases its mass, which increases the energy required to accelerate and decelerate it, which increases the size of the propulsion system, which increases the mass further. The life support systems must be scaled to support not just the crew, but the workers who operate the factories. The factories must produce parts not just for life support but for the propulsion system, the navigation system, the structural hull, and the factories themselves. Every addition to the ship's capability adds mass, complexity, and additional failure modes that must themselves be managed. The design spirals outward, each solution creating new requirements that demand further solutions. This is why serious proposals for generation ships or world ships describe vessels measured not in meters but in kilometers. The Chrysalis design, winner of the 2025 Project Hyperion competition organized by the Initiative for Interstellar Studies, envisions a modular habitat structure designed for 500 to 1,500 people on a 250-year mission. Even this relatively short duration, small population concept pushes the boundaries of what current and near-future engineering could plausibly achieve. Scaling to a 10,000-year mission with a genetically viable population of tens of thousands of people would require a vessel so large that it enters the category sometimes called a world ship, a structure potentially tens of kilometers in length, with internal volumes comparable to a small enclosed city. Building, launching, and accelerating such a structure represents an energy expenditure that exceeds the total current annual energy output of human civilization by orders of magnitude. And even a vessel of this enormous scale faces the same fundamental problem. Everything within it degrades. Every system requires maintenance. Every component requires eventual replacement. Every replacement requires manufacturing. Every manufacturing process requires raw materials, energy, knowledge, and human labor. The chain must never break. Not once. Not for 10,000 years. The machine that carries the generation ship's passengers is not a vehicle in any meaningful sense. It is an industrial ecosystem, a self-repairing, self-manufacturing artificial world that must operate without external input for a duration longer than any machine, any factory, any industrial process in human history has ever functioned. It must do this while simultaneously keeping its biological passengers alive, fed, hydrated, breathing, shielded from radiation, and anchored to its spinning floors by artificial gravity generated through continuous mechanical rotation. But even if this machine could be built, even if every bearing could be replaced and every reactor refueled and every seal remanufactured for 10 millennia without interruption, the ship would still face a problem that no amount of engineering can solve with hardware alone. Because the passengers are not cargo, they are not inert payloads riding passively inside the hull. They are living, thinking, reproducing, aging, disagreeing, forgetting, grieving, rebelling, creating, and changing human beings, and keeping a human population biologically viable, genetically healthy, medically sustained, socially organized, educationally competent, psychologically stable, and culturally coherent. For 400 generations of unbroken confinement inside a sealed vessel may be the single most difficult challenge in the entire generation ship problem. What comes next reveals why the ship's human passengers, the very reason the mission exists, may be the greatest threat to its survival. Strip away the engineering, set aside the reactors, the bearings, the seals, the radiation shielding, the atmospheric processors, and the water recycling loops. Imagine, for a moment, that every machine aboard the generation ship works perfectly for the entire 10,000-year journey. Every pump runs without failure. Every reactor generates power on schedule. Every agricultural bay produces food. Every waste processor converts biological refuse into clean nutrients. The hull holds, the shielding endures. The thermal radiators shed heat into the void without degradation. Grant the engineers their miracle. The ship still faces a problem that no machine can solve. The passengers are human, and humans, across 10,000 years of confinement in a sealed vessel, will do what humans have always done. They will reproduce, they will age, they will get sick. They will disagree about how to raise their children, how to distribute food, who should hold authority, and whether the mission is worth continuing. They will forget things their grandparents knew. They will invent stories about things that never happened. They will form factions. They will fall in love with people the geneticists did not intend for them. They will refuse orders. They will grieve. They will get bored. And across 400 generations of this irreducibly human behavior, the biological, social, and cultural fabric of the ship's population will drift, warp, tear, and reconstitute itself in ways that no mission planner can predict or control. Begin with genetics, because genetics is the quietest catastrophe. It operates below the threshold of daily awareness, invisible to any individual, measurable only across generations, and by the time its effects become obvious, the damage may be irreversible. A generation ship carries a closed population. No one enters from outside. No one brings fresh genetic material from a distant continent or a neighbouring community. Every child born aboard the ship draws its entire genetic inheritance from the existing population, and only from the existing population, for the full duration of the journey. In population genetics, this is called a closed breeding population, and it is subject to forces that relentlessly erode genetic diversity over time. The most immediate threat is inbreeding. In a small population where everyone is related to everyone else within a few generations, mating between individuals who share recent common ancestors becomes statistically inevitable. Inbreeding increases the probability that a child inherits two copies of the same recessive allele, one from each parent, unmasking harmful mutations that would remain hidden in a larger, more genetically diverse population. The consequences are well documented in human communities that have experienced prolonged genetic isolation. Among the Old Order Amish, whose founding population in North America numbered only a few hundred individuals, certain rare genetic disorders occur at rates far above the general population average. Among Ashkenazi Jewish communities, which experienced severe population bottlenecks during historical persecutions, diseases like Tay-Sachs appear at elevated frequencies. These are not ancient populations. They have been genetically restricted for mere centuries, not millennia. The generation ship would maintain its genetic closure for far longer. The question of how many people a generation ship must carry to avoid catastrophic inbreeding has been studied repeatedly, and the answers vary enormously depending on the assumptions. In 2018, astrophysicist Frederick Marin and colleagues published simulations suggesting that a minimum crew of 98 individuals, supplemented by a cryogenic bank of preserved sperm, eggs, and embryos, could maintain sufficient genetic diversity across a multi-generational voyage to Proxima Centauri. This estimate assumes strict reproductive management, with mating pairs selected to maximize genetic distance between partners. It also assumes the cryogenic reserves remain viable for the full journey, which is itself a significant assumption given the challenges of maintaining biological samples at ultra-low temperatures for centuries or millennia in a radiation-saturated environment. At the other end of the range, anthropologist Cameron Smith published an analysis in 2014 arguing that a genetically viable population for a multi-generational voyage requires between 10,000 and 40,000 individuals. Smith's estimate accounts not only for raw genetic diversity, but for the need to maintain cultural diversity, adaptive behavioral variance, and resilience against catastrophic population loss from epidemics, accidents, or social violence. His calculation incorporates the reality that human populations do not mate randomly. People choose partners based on proximity, social status, physical attraction, cultural affinity, and dozens of other factors that systematically reduce the effective breeding population below the total headcount. In a population of 10,000, the effective breeding population, the number of individuals actually contributing genes to the next generation, might be less than half that number. The gap between 98 and 40,000 is not a minor academic disagreement. It represents fundamentally different visions of what a generation ship must be. A ship carrying 100 people is a vessel. A ship carrying 40,000 people is a city. The mass, volume, life support capacity, food production requirements, and energy demands scale accordingly. And the question of which estimate is correct cannot be answered definitively, because humanity has never attempted anything remotely similar. Both figures are extrapolations from population genetics theory, computer simulations, and observations of small human communities on Earth, none of which perfectly replicate the conditions aboard an interstellar vessel. Beyond inbreeding, a closed population faces genetic drift, the random fluctuation in allele frequencies that occurs in every generation. In large populations, drift is negligible because statistical averaging smooths out random variations. In small populations, drift is powerful. Beneficial alleles can be lost by pure chance. Harmful alleles can become fixed, meaning every individual in the population carries them, simply because random sampling happened to favor their transmission. Over 10,000 years, genetic drift could reshape the ship's population in unpredictable ways, eliminating genetic variants that might later prove essential for adapting to conditions on the destination planet. Radiation compounds the genetic problem. As we have seen, galactic cosmic rays continuously damage DNA in every cell of every organism aboard the ship. Most of this damage is repaired by cellular mechanisms, but repair is not perfect. Some mutations persist, and when they occur in reproductive cells, they are inherited by the next generation. In a population receiving fresh immigration from genetically diverse external sources, these mutations are diluted and selected against over time. In a closed population, they accumulate. Each generation inherits not only the mutations arising in its own lifetime, but the entire burden of mutations accumulated by every previous generation. The rate of accumulation depends on population size, radiation dose, and the efficiency of biological repair mechanisms, but the direction is always the same. The mutational load grows. Over hundreds of generations, the cumulative genetic damage could manifest as declining fertility, increased rates of developmental abnormalities, reduced immune competence, and a gradual erosion of the population's overall biological fitness. Managing this genetic burden requires active intervention. The ship's medical and genetic infrastructure must monitor the population's genome across generations, identify harmful mutations before they become fixed, and implement reproductive strategies that minimize inbreeding and maximize genetic diversity. This means the ship must carry not just doctors but geneticists, not just a hospital but a genetic screening laboratory, and not just reproductive freedom but a managed reproduction program that balances individual autonomy against population-level genetic health. The ethical dimensions of such a program are staggering. Who decides which individuals should reproduce together? How much reproductive freedom can be permitted before genetic drift becomes dangerous? What happens when the genetically optimal pairing involves two people who do not wish to have children together? These are not hypothetical philosophical dilemmas. They are operational decisions that must be made, enforced, and accepted by the population for every generation of the voyage. Disease presents a different category of biological threat. The ship is a sealed container, holding thousands of human beings alongside every microorganism they carry on their skin, in their intestines, in their respiratory tracts, and in the soil of their agricultural systems. Bacteria, viruses, fungi, and parasites are not optional passengers. They are integral components of human biology and agricultural ecology. Many of them are beneficial or neutral under normal conditions. But in a closed environment with a finite population and no access to external medical resources, the dynamics of infectious disease change dramatically. On Earth, epidemics burn through populations and eventually subside because the pathogen runs out of susceptible hosts. because geographic distance limits transmission, because medical infrastructure provides treatment, or because genetic diversity within the population ensures that some individuals possess natural resistance. On a generation ship, none of these buffers exist in adequate measure. Geographic distance between individuals is measured in meters, not kilometers. The entire population shares the same air supply, the same water recycling system, and the same food production infrastructure. Medical resources are limited to what the ship carries and can manufacture, and genetic diversity, as discussed, is constrained by the small founding population. A novel pathogen emerging within the ship's population, whether through mutation of an existing microorganism, through contamination from agricultural soil, or through the evolution of a benign commensal organism into a virulent form, could spread through the entire vessel within days. If the disease is lethal to even a moderate fraction of those infected, the consequences are catastrophic in a way that has no terrestrial parallel. A pandemic that kills 10% of a nation of 100 million people is a horrific tragedy. But the nation survives with 90 million people and intact infrastructure. A pandemic that kills 10% of a ship's population of 10,000 people kills 1,000 individuals, potentially including irreplaceable specialists in reactor maintenance, agricultural management, medical care, or navigation. The ship does not have neighbouring countries to send aid. It does not have reserve populations to fill critical roles. It does not have pharmaceutical factories producing millions of doses of a new vaccine. Every death aboard the ship is a permanent loss to a system with no external replenishment. Quarantine, the most basic tool for containing epidemics, faces severe limitations aboard a vessel where all inhabitants share interconnected atmospheric and water systems. Sealing off a section of the ship might slow transmission, but the air recycling infrastructure was designed to serve the entire vessel as an integrated system. Isolating a compartment means either cutting it off from life support, which endangers its inhabitants, or maintaining parallel life support systems with sufficient independence to prevent pathogen transfer, which represents an enormous additional engineering burden. But the threat is not limited to diseases that already exist at launch. The ship's microbiome will evolve. Bacteria reproduce on timescales measured in minutes and hours, not decades. A single bacterial species can cycle through hundreds of thousands of generations during a single human generation aboard the ship. Under the constant selective pressure of a closed environment, with a fixed population of hosts, a limited range of antibiotics, and no influx of competing microbial strains from external sources, the evolutionary trajectory of the ship's microbial ecosystem becomes deeply unpredictable. On Earth, human immune systems are continuously trained by exposure to a vast and constantly shifting landscape of microorganisms encountered through contact with soil, water, animals, other human populations, and the open environment. This exposure keeps immune responses calibrated, diverse, and adaptable. Inside a generation ship, the microbial environment is static compared to Earth's. The same strains circulate through the same population, in the same enclosed habitat, generation after generation. Without novel immune challenges, the population's collective immune competence could narrow over centuries, becoming highly effective against the specific organisms present aboard the ship, but increasingly vulnerable to anything unfamiliar. Meanwhile, the organisms themselves are not standing still. Commensal bacteria, the species that normally coexist harmlessly with their human hosts, can drift toward virulence under conditions of sustained interaction with a genetically narrowing host population. A strain of gut bacteria that is harmless for 500 years might, through accumulated mutations and horizontal gene transfer with other shipboard microbes, acquire characteristics that allow it to colonize new tissues, resist existing treatments, or trigger immune responses. Its hosts are no longer equipped to manage. The ship does not need to encounter an alien pathogen. It can grow its own, slowly, silently, across the very time scale that makes every other problem aboard the vessel so dangerous. The ship must therefore maintain a medical establishment capable of diagnosing novel diseases, developing treatments, producing pharmaceuticals from onboard chemical feedstocks, manufacturing medical equipment, training new physicians and researchers, and conducting the kind of epidemiological surveillance that on Earth employs thousands of professionals across national health agencies. This medical infrastructure must function without interruption for 10,000 years, adapting to new diseases as they emerge, because microbial evolution does not stop aboard a sealed vessel. If anything, it accelerates in a closed environment where the same population of hosts and pathogens interacts continuously under constant selective pressure. But genetics and disease, as serious as they are, address only the biological dimension of the human problem. The civilizational dimension may be even harder to solve, because it involves the most complex and unpredictable system in the known universe: human social behavior. Governance aboard a generation ship must accomplish something no political system in human history has achieved. It must maintain stable, functional, legitimate authority across 400 consecutive generations without a single period of collapse, civil war, tyranny so severe that critical systems are neglected, or anarchy so thorough that maintenance schedules are abandoned. Every form of government humanity has ever practiced has eventually failed, been overthrown, reformed, or replaced. Democracies have fallen to demagogues. Monarchies have been toppled by revolutions. Theocracies have fractured into sectarian violence. Military juntas have collapsed under their own corruption. Communist states have dissolved. Empires have crumbled. The average lifespan of a political system, measured from founding to fundamental restructuring, is a few centuries at most. The generation ship requires continuous functional governance for 50 to 100 times that duration. What happens when a faction aboard the ship decides that the current government is illegitimate? On Earth, dissatisfied populations can emigrate, secede, or appeal to external powers. On a generation ship, there is nowhere to go. Every person aboard is trapped within the same hull, breathing the same air, eating food grown in the same agricultural bays. Political conflict that on Earth might result in a border dispute or a trade embargo could on a ship result in sabotage of life support systems, seizure of food production facilities, or deliberate damage to critical infrastructure. A civil war aboard a generation ship is not a political event. It is an existential threat. Combatants cannot destroy the enemy's territory without destroying their own life support. Yet the psychological pressures that drive political violence, grievance, inequality, perceived injustice, competition for scarce resources, ideological fanaticism, do not disappear because the stakes are higher. If anything, the confinement and the impossibility of escape intensify them. The ship must therefore develop not just a government, but a political culture, a deeply internalized set of norms, values, and conflict resolution mechanisms that prevent disputes from escalating to the point where critical systems are threatened. This political culture must be robust enough to survive the inevitable stresses of scarcity, interpersonal conflict, generational change, and the slow accumulation of grievances over millennia. It must be flexible enough to adapt to changing circumstances without losing its core commitment to the ship's survival. And it must be transmitted, intact and functional, to every new generation through education, socialization, and lived experience. Education is the transmission mechanism for everything the ship needs to survive. Every generation must learn the technical skills required to maintain the vessel, from reactor operation to agricultural management, to medical practice, to manufacturing technology. Every generation must learn the scientific principles underlying those skills, because rote procedure without understanding cannot adapt to novel failures. Every generation must learn the ship's history, its mission, its purpose, and the reasons why the journey was undertaken. Every generation must learn the social norms, governance principles, and conflict resolution practices that keep the community functional. And every generation must learn all of this well enough to teach it to the next generation with sufficient fidelity that critical knowledge is not lost or distorted. This is the knowledge preservation problem, and on a 10,000-year timescale, it is genuinely terrifying. Human knowledge transmission is imperfect, even under ideal conditions. Every act of teaching introduces small errors, simplifications, misunderstandings, and reinterpretations. Over a few generations, these distortions are minor. Over dozens of generations, they accumulate. Over hundreds of generations, they can transform the original knowledge beyond recognition. Consider how much the English language has changed in just 1,000 years. Old English, spoken around the year 1000, is mutually unintelligible with modern English. A crew member from the launch generation, transported forward 1,000 years aboard the ship, would be unable to understand the language spoken by the crew at that point. Over 10,000 years, the language could change so dramatically that the original mission documents, the engineering schematics, the scientific textbooks, the maintenance manuals would become as unreadable as Sumerian cuneiform is to a modern English speaker. Written records help, but they do not solve the problem. Records must be stored on media that survive millennia. Paper decays, magnetic storage degrades, optical media deteriorates under radiation exposure. Even stone tablets, the most durable information storage medium ever used by humans, suffer erosion and damage over thousands of years. The ship must maintain its archives through active curation, periodically copying information from degrading media to fresh media, translating documents into the evolving contemporary language, and ensuring that every generation has both the tools to access the archives and the training to understand their contents. If a single generation neglects this curation, decades or centuries of accumulated records could become inaccessible. If the curation process itself introduces errors, the knowledge base slowly corrupts, like a document photocopied from a photocopy from a photocopy, until the original text is illegible. Religion and mythology pose a particularly subtle threat to knowledge preservation. Humans are storytelling creatures. We instinctively embed information in narratives, and narratives evolve with each retelling. Over generations, factual accounts of the ship's construction and launch could merge with mythological elements. The engineers who designed the vessel could become legendary figures with superhuman attributes. The purpose of the mission could be reinterpreted through religious frameworks that the original planners never intended. The destination star could become a promised land, described in spiritual rather than astronomical terms. The technical procedures for operating critical systems could become rituals performed out of tradition rather than understanding, their scientific basis forgotten even as the motions are faithfully reproduced. This process is not hypothetical. It is exactly what has happened to knowledge transmission in every long-lived human culture. Ancient astronomical observations became embedded in myths. Nothing, practical agricultural techniques became associated with religious ceremonies. Medical knowledge was transmitted through healing rituals that preserved some effective practices while mixing them with ineffective or harmful ones. On Earth, this cultural drift has consequences that societies can survive because the planet itself provides the resources needed for life, regardless of whether its inhabitants understand why. On a generation ship, where every life-sustaining process depends on deliberate human action informed by accurate technical knowledge, the drift from understanding to ritual could be fatal. The psychological dimension of confinement adds further strain. Human beings evolved in open environments, under skies that changed with the weather and seasons, surrounded by landscapes that extended to the horizon. The generation ship offers none of this. Its inhabitants live inside a sealed structure with artificial lighting, recycled air, and views that extend no farther than the opposite wall of their habitat module. The longest sightline aboard even the most generously designed ship is measured in hundreds of meters, not kilometers. There is no weather except what the environmental systems produce. There is no horizon. There is no outside. research on human psychology in confined environments, drawn from submarine deployments, Antarctic overwinter stations, and space station missions, consistently identifies a cluster of problems associated with long-duration isolation and confinement. These include depression, anxiety, interpersonal conflict, social withdrawal, sleep disruption, cognitive decline, and what psychologists call the third quarter phenomenon, a period of declining morale and increased conflict that typically occurs when participants realize they have passed the midpoint of their confinement but still face a long period before release. On a generation ship, there is no midpoint and there is no release. The confinement is permanent. The inhabitants are not volunteers enduring a difficult assignment with an end date. They are people born into a sealed environment who will live their entire lives and die inside it. Their children will do the same, and their grandchildren, for 400 consecutive generations. What does this do to a human population over millennia? No experiment has ever been conducted at this timescale, so any answer involves extrapolation. But the available evidence suggests that chronic confinement produces chronic psychological strain, and chronic psychological strain produces behavioral changes that affect every aspect of community function. Increased aggression, decreased cooperation, reduced motivation, impaired decision-making, elevated rates of substance abuse and self-harm. These are documented outcomes of prolonged confinement in even well-supported environments with professional psychological care and the knowledge that the confinement will end. Remove the endpoint and the effects could be profoundly worse. The ship must therefore maintain a psychological support infrastructure, not a counselling office but an entire mental health system, across the full duration of the journey. This system must be staffed, funded, supported, and integrated into the ship's culture in a way that prevents the accumulation of untreated psychological damage across generations. It must adapt to the evolving psychological landscape of a population that has no living memory of open skies and no expectation of ever experiencing them. There is a dimension of this confinement that goes beyond documented psychological disorders and into territory no researcher has been able to study, because no human population has ever lived it. Every person aboard the generation ship will be born inside a structure with hard boundaries. They will never see an unobstructed horizon. They will never feel wind that was not generated by a fan. They will never hear thunder or rain falling on a surface larger than a habitat module. They will never look upward and see a sky that extends beyond comprehension. The longest distance their eyes will ever focus on is the far wall of the ship's largest interior space, perhaps a few hundred meters away. Beyond that wall, they know intellectually, lies the void of interstellar space, but they will never perceive it directly, because looking out would mean looking at nothing, an absolute darkness with no landmarks, no motion, and no reference points, possibly more psychologically disturbing than the enclosure itself. Human spatial cognition evolved in open landscapes. The brain's navigation systems, its sense of place, its capacity for spatial memory and orientation, developed over hundreds of thousands of years in environments where horizons stretched for kilometers and the sky formed an infinite dome overhead. These systems do not switch off when the environment shrinks. They continue operating, processing spatial information from an environment that provides almost none of the cues they were designed to interpret. What this does to human cognition across a single lifetime is largely unknown. What it does across hundreds of generations of people who have never known anything else is entirely uncharted. The children born aboard the ship will not miss open spaces because they will never have experienced them, but their neural architecture will still carry the evolutionary legacy of a species shaped by savannas, forests, coastlines, and mountain ranges. Whether that architecture can adapt to permanent enclosure without cost, whether spatial reasoning, creative cognition, emotional regulation, and social behavior remain unaffected when the environment that shaped them is permanently absent, is a question that no generation ship designer can answer with confidence. The honest answer is that no one knows. And the generation ship demands that we bet 10,000 years of human continuity on the hope that the answer is favourable. And then there is the question that sits beneath all the others, the question that no amount of engineering, genetics, medicine, governance, education, or psychological support can fully answer. The question of consent. The first generation aboard the ship chose to be there. They volunteered. They understood the mission, accepted the risks, and made a deliberate decision to leave Earth and spend their remaining years inside a vessel, heading for another star. They chose the mission for themselves and, implicitly, for their descendants. But their descendants did not choose. The children born aboard the ship had no say in the matter. They did not volunteer. They were not consulted. They were born into a sealed container hurtling through interstellar space, and they will die inside that container, and their only legacy will be children who inherit the same unchosen fate. This is not a temporary injustice that resolves itself when the journey ends. For the overwhelming majority of the ship's inhabitants, across hundreds of generations, the journey is their entire existence. They will never see the destination. They exist solely to maintain the ship and produce the next generation of maintainers. Their lives are instrumental, serving a purpose defined by ancestors who are centuries or millennia dead. How does a society maintain commitment to a mission that none of its living members chose and that none of them will see completed? On Earth, long-term projects like cathedral construction sometimes spanned multiple generations, but the builders lived in open societies with countless other sources of meaning, purpose, and identity. The cathedral was a project, not a prison. The builders could walk away. The generation ship's inhabitants cannot walk away. The mission is not a project they are working on. It is the totality of their existence. If they reject the mission, they have nowhere to go. If they embrace it, they are embracing a life of service to a goal defined by people they never met. Some generations might embrace the mission fervently, treating it as a sacred calling and dedicating their lives to the ship's maintenance with passionate devotion. Other generations might resent it, viewing themselves as prisoners condemned to serve a sentence imposed by their ancestors. Still others might simply lose interest, treating the mission as irrelevant background noise while focusing on their immediate personal concerns, letting maintenance schedules slip, allowing educational standards to decline, permitting governance structures to weaken. Any of these responses, sustained across enough generations, could threaten the mission's survival. Fervent devotion could produce rigidity and intolerance of dissent. Resentment could produce sabotage or revolution. Apathy could produce neglect of critical systems. The ship must somehow cultivate and maintain, across 400 generations, a relationship between its inhabitants and its mission that is healthy, sustainable, and resilient, not fanatical, not resentful, not apathetic. Something that gives meaning to lives lived entirely within a sealed vessel, without becoming so brittle that it shatters when challenged by changing circumstances or generational attitudes. No human institution has ever accomplished this. Every organization that has lasted more than a few centuries, the Catholic Church, the oldest universities, the longest-running governments, has done so by continuously adapting its message, its structure, and its practices to the changing values of successive generations. The ship must do the same, but it must do so without ever losing the technical competence and social cohesion required to keep its life support systems running. It must evolve culturally while maintaining operational continuity. It must change without breaking. The crew of a generation ship does not face one existential problem. It faces a convergence of existential problems operating simultaneously across every dimension of human experience. Genetic erosion, epidemic disease, political instability, knowledge decay, psychological deterioration, loss of purpose. Each of these problems is manageable in isolation over short timescales. Together, over 10,000 years, They form a web of interacting risks where a failure in any one domain cascades into every other domain. A political crisis disrupts education. Educational decline impairs maintenance capability. Maintenance failure degrades life support. Life support degradation triggers food shortages. Food shortages exacerbate political tensions. The cycle feeds on itself, and in a closed system with no external support, the spiral can only be broken by the people inside the ship, using only the resources and knowledge they possess at the moment the crisis strikes. What remains is the question that everything before this has been building toward. If the machines can be maintained, if the ecology can be sustained, if the population can be kept genetically viable, if the diseases can be managed, if the governance can be preserved, if the knowledge can be transmitted, if the psychology can be supported, and if the mission can retain its meaning across 400 unbroken generations of people who never chose it, then what arrives at the destination? Is it the same civilization that launched? Is it the same species? Is it something that the founders would recognize, or something so changed by 10,000 years of drift, adaptation, isolation, and reinvention that the word human barely applies? What follows asks whether the ship that survives is still carrying what it set out to deliver. There is a number that haunts engineers, and it is not a distance or a speed. It is a probability. Specifically, it is the probability that a complex system will survive without a catastrophic failure over a given period of time. This number, expressed as system reliability, determines whether machines work, whether bridges stand, whether aircraft land safely, and whether a generation ship delivers its passengers alive. Take a single system with a reliability of 99.9% per year. That means, in any given year, there is only a 1 in 1,000 chance that this system will experience a critical failure. By any ordinary engineering standard, this is exceptional. Commercial aircraft achieve reliability figures in this range for individual critical components, and aviation is considered the safest form of long-distance travel ever devised. A system this reliable would operate for years, probably decades, before encountering a serious problem. Now run that system for 10,000 years. The mathematics is straightforward. The probability of surviving 1 year without failure is 0.999. The probability of surviving 2 years is 0.999, multiplied by itself. The probability of surviving 10,000 years is 0.999, raised to the power of 10,000. The result is approximately 0.000005. That is a survival probability of less than 1/100th of 1%. A system that is 99.9% reliable in any single year has virtually no chance of lasting 10,000 years without a critical failure. Increase the reliability to 99.99% per year. One failure chance in 10,000. Over 10,000 years, the survival probability rises to approximately 37%. Better, but still worse odds than a coin flip. Push the reliability to 99.999%. One chance in 100,000 per year, and the 10,000-year survival probability reaches approximately 90%. This sounds reassuring until you realize that a generation ship does not depend on a single system. It depends on thousands of interdependent systems, each of which must survive for the full journey. If the ship contains just 1,000 critical systems, each with 99.999% annual reliability, the compound probability that every single one of them survives 10,000 years without failure does not drop to a small number. It drops to a number so close to zero that writing it out would require more than 40 zeros after the decimal point before reaching the first meaningful digit. 1,000 highly reliable systems, and the compound probability of total mission survival is not merely low. It is mathematically indistinguishable from impossible without continuous repair. This is not a flaw in the engineering. This is a law of mathematics. Any system composed of finite lifespan components, no matter how reliable those components are individually, will eventually fail if operated long enough. The only way to survive is to repair failures as they occur, replacing worn components before cascading breakdowns propagate through interconnected systems. The generation ship does not need perfect components. It needs a perfect maintenance civilization, a population that detects, diagnoses, and repairs every failure in every system aboard the vessel without interruption for 10 millennia. The components are allowed to fail, the repair process is not. This means the true reliability bottleneck is not the hardware. It is the human capacity to maintain the hardware. And human capacity, unlike mechanical reliability, cannot be expressed as a fixed annual percentage. It fluctuates. It depends on training, motivation, social stability, resource availability, institutional continuity, and 100 other variables that themselves change across generations. A generation with excellent technical education and strong institutional support will maintain the ship competently. A generation weakened by epidemic disease, political upheaval, educational decline, or simple cultural drift away from technical priorities may miss critical maintenance windows. A single generation of deferred maintenance, even a single decade, could allow cascading failures that overwhelm the repair capability of subsequent generations. The analogy is not a machine that must be kept running. The analogy is a juggler who must keep 10,000 balls in the air, simultaneously, without dropping a single one, for 10,000 years, while being periodically replaced by a new juggler who must learn the pattern from the outgoing one without ever letting a ball touch the ground. The skill can be taught, the knowledge can be transmitted, but a single fumbled handoff, a single generation that fails to learn the pattern with sufficient precision, and balls begin to fall. Once enough balls are on the ground, the remaining pattern becomes unstable. Recovery becomes impossible. Consider what a single century of reduced maintenance capability could produce. Atmospheric monitoring sensors drift out of calibration. Undetected, carbon dioxide levels rise slightly in certain compartments. Crop yields decline in those areas because the atmospheric adjustment systems are not compensating for the shift. Food production drops by a few percent. The population begins drawing on reserves. Meanwhile, a bearing in one of the water recycling centrifuges shows early signs of fatigue. The maintenance team, understaffed because the educational system in the previous generation produced fewer engineers than needed, defers the repair in favor of more pressing tasks. The bearing fails 18 months later. The centrifuge goes offline. Water recycling capacity drops. Rationing begins. Social tensions rise as water allocation becomes a political issue. A dispute between habitat sections over water access escalates into a refusal to cooperate on shared maintenance tasks. Critical cross-section maintenance is delayed further. Another system degrades. The cascade deepens. None of these individual failures is catastrophic. Each one, in isolation, is recoverable. But in combination, across years and decades of compounding neglect, they create a degradation spiral that feeds on itself. Reduced maintenance capability produces system failures. System failures consume the remaining maintenance capacity. Consumed maintenance capacity prevents attention to other systems. Other systems begin failing. The ship does not die from a single wound. It dies from 1,000 small cuts, each one survivable, their accumulation lethal. And the cuts are not limited to hardware. Cultural drift operates on the same timescale, with the same cumulative mathematics, and with consequences that are equally irreversible once they pass a critical threshold. Language is the most fundamental medium of knowledge transmission, and language never stands still. Every living language changes continuously. Pronunciation shifts. Grammar simplifies or restructures. Vocabulary expands in some domains and contracts in others. New words are coined while old words fall out of use. On Earth, these changes are driven by contact between communities, migration, technological innovation, cultural exchange, and the natural creativity of speakers adapting their language to changing circumstances. On a generation ship, the drivers of change would be different, shaped by the unique environment, the specialized vocabulary of shipboard life, and the social dynamics of a closed community, but the process would be no less relentless. As explored earlier, the ship's living language would become unintelligible to the launch generation within 1,000 years and unrecognizable within 5,000. Technical vocabulary would shift meaning or disappear. No preserved language program, not even one modeled on Latin's long tenure, has ever been sustained across 400 generations. Religion and ideology undergo similar transformations. The founding generation might be secular scientists motivated by curiosity and the survival of the species. Their grandchildren might maintain that secular outlook, but across dozens of generations, spiritual and ideological frameworks inevitably arise, evolve, compete, and replace one another. Human beings generate meaning-making narratives as naturally as they generate language. In a closed environment where the only shared experience is life aboard the ship, new belief systems will crystallize around the ship itself, its history, its mission, its origin story, and the nature of the universe outside the hull. Within a few centuries, the founding of the ship could become a creation myth. The launch from Earth could be described in terms more theological than historical. The engineers who designed the vessel could be elevated to the status of divine or semi-divine figures. The destination star could become a paradise, a promised land, or a test of faith, depending on the religious framework that emerges. The maintenance of the ship's systems could be ritualized, with procedures performed out of sacred obligation rather than technical understanding. This might actually help preserve some practices across generations, since ritual is remarkably persistent. But ritual without understanding is brittle. When a ritualized procedure encounters a situation the original designers did not anticipate, a crew that understands the underlying science can improvise. A crew that only knows the ritual cannot. The inverse is equally dangerous. A generation that develops a belief system fundamentally opposed to the mission, one that views the ship as a prison, the mission as a crime committed by ancestors against descendants, or the destination as a deception, could deliberately or passively resist the maintenance activities required for survival. If such a belief system gains enough adherents, and if the ship's governance structure lacks the authority or legitimacy to compel compliance, critical systems could be neglected not through incompetence, but through ideological conviction. The mission could fail not because the ship's inhabitants forgot how to maintain it, but because they chose not to. And then there is the deepest question, the one that everything before this has been building toward. What arrives? Assume the best case. Assume the ship survives. Assume the machinery is maintained. The ecology is balanced. The population is genetically viable. The diseases are managed. The governance is stable. The education is effective, the knowledge is preserved, and the mission retains its purpose across every one of the 400 generations required to traverse 10,000 years of interstellar space. The ship decelerates. It enters orbit around the destination star. The passengers prepare to descend to a planet's surface. They open the doors. Who steps out? The people who emerge from the ship will have been shaped by 10,000 years of selective pressures, cultural evolution, and biological change that no one at launch could have predicted. They will have lived their entire evolutionary history in artificial gravity, recycled air, controlled lighting, and a social environment radically different from anything experienced by any human population on Earth. Their bodies will have adapted to the specific gravitational loading of the ship's rotation, which may differ subtly from the gravity of the destination planet. Their immune systems will have been calibrated to the particular microbial ecosystem aboard the vessel, not to the novel microorganisms that may exist on an alien world. Their skin will have adapted to artificial lighting rather than the spectrum of a natural star. Their psychological responses will be tuned to enclosed spaces, predictable environments, and the social norms of shipboard culture, not to open skies, weather, wildlife, and the infinite unpredictability of a planetary surface. Genetically, the arriving population will differ from the founding population. 10,000 years of genetic drift, radiation-induced mutation, and selection under shipboard conditions will have shifted allele frequencies in ways that are impossible to predict but guaranteed to be significant. The population that lands may be more resistant to radiation and less resistant to ultraviolet light. It may have altered metabolic responses to diet. It may carry fixed alleles for traits that were neutral or slightly beneficial aboard the ship but deleterious on a planet's surface. It will almost certainly have reduced genetic diversity compared to the founding population, limiting its capacity to adapt to novel environmental challenges. Culturally, the people who step off the ship will be products of a civilization that has no institutional memory of what life on a planetary surface actually involves. They will have read about wind in their archives. They will have studied images of oceans. They will have learned about weather in their schools. But none of them, and none of their ancestors for hundreds of generations, will have experienced any of these things directly. The sky will be a concept they understand intellectually but have never seen. Open space extending to a horizon will be a disorienting, possibly terrifying experience for people whose entire perceptual world has been bounded by walls measured in hundreds of meters. Rain falling on their skin will be a sensation unlike anything in their experiential vocabulary. The sounds of a living planet, wind, water, animals, thunder, will be alien to ears attuned to the hum of ventilation systems and the rhythmic cycling of machinery. The language they speak will not be the language spoken on Earth, if Earth still has a civilization sending or receiving communications. Their social customs, their art, their music, their cuisine, their religious beliefs, their governance structures, their family organizations, their concepts of privacy, authority, beauty, humor, and meaning will all be products of 10,000 years of independent cultural evolution inside a sealed container. They will be as culturally distant from the launch generation as modern humans are from the people who painted on cave walls during the last ice age. They will be human, probably, in the biological sense. But they will not be the same humans who boarded the ship. They will be something new, something shaped by the ship, by the voyage, by the unique selective pressures of confinement, isolation, and artificially maintained existence across a span of time that dwarfs the entire history of terrestrial civilization. This raises a question that is less scientific than existential, but it is the question that defines the entire generation ship problem. If the people who arrive at the destination are so changed by the journey that they bear only biological kinship to the people who launched, has the mission succeeded? If the civilization that steps onto an alien world shares nothing with 21st century humanity except its DNA, and even that has been altered by millennia of drift and mutation, what exactly has been preserved? What has been transported across the stars? One answer is that the mission was never about preserving a specific culture. It was about preserving life. The generation ship carries biological humanity forward, not cultural or institutional continuity. By this measure, success means arrival of a viable breeding population, regardless of what language they speak, what they believe, or how they organize their society. Life persists. The species continues. The specific cultural content is irrelevant. Another answer is that this reduces the mission to mere biological reproduction, which any sufficiently robust frozen embryo bank could accomplish more cheaply and more reliably. If the goal is only to deposit human DNA on another planet, a generation ship is a spectacularly inefficient way to achieve it. The generation ship's unique value proposition is that it carries not just human bodies but a human civilization, a functioning society capable of landing on an alien world and building a new branch of humanity from the first day. If that civilization has been so transformed by the journey that it cannot function on the destination planet, or if it has lost the knowledge and social cohesion needed to establish a colony, then the generation ship has failed in exactly the way it was designed to prevent. There is a deeper and more unsettling possibility. Perhaps the generation ship does not fail. Perhaps it succeeds too well. Perhaps the ship becomes so self-sufficient, so culturally complete, so thoroughly adapted to its own internal environment that its inhabitants no longer wish to leave. After 10,000 years, the ship is not a vehicle approaching a destination. It is home. It is the only world its people have ever known. The destination planet is not a promised land. It is a terrifyingly alien environment. Open, uncontrolled, unpredictable, filled with unknown microorganisms, bathed in unfiltered radiation from an unfamiliar star, subject to weather and geological processes that the ship's inhabitants have studied but never experienced. Stepping off the ship onto an open planetary surface would require a psychological and cultural transformation as profound as the original decision to leave Earth. The ship's inhabitants might conclude, quite rationally, that they are better adapted to their artificial world than to any natural one. They might choose to stay aboard, they might continue flying. This is not failure in the traditional sense. The ship survived, the population survived, the civilization survived. But the mission, as originally conceived by the launch generation, has been abandoned by descendants who feel no obligation to honor commitments made by ancestors they never knew, in a language they cannot read, for reasons they no longer understand. The ship set out to reach a star. Instead, it became a world unto itself, drifting through interstellar space, complete, autonomous, and uninterested in landing. A generation ship is not a spacecraft. This is the conclusion that every line of evidence, from population genetics to atmospheric chemistry to materials science to political theory, converges upon. A spacecraft is a vehicle that carries passengers from one location to another. It has a departure, a journey, and an arrival. The passengers who board are the passengers who disembark. The journey is an interruption in their lives, not the entirety of their existence. A generation ship is none of these things. It is a civilization sealed inside a machine, and the machine is sealed inside a universe that offers it nothing. No air, no water, no food, no raw materials, no gravity, no shielding, no help, no rescue, no companionship, no contact with any other human society, no confirmation that Earth still exists, no assurance that the destination is habitable, no guarantee that the stars have not shifted, that the navigation is correct, that the target planet is what the original surveys suggested it might be. The ship and its people are utterly, cosmically alone, and they must remain alone and functional and intact and purposeful for longer than the Great Pyramid of Giza has been standing, longer than the oldest living tree has been growing, longer than any continuously occupied city has been inhabited, longer than any written script has been read, longer than any spoken language has persisted in recognizable form. The ship must outlast everything that humanity has ever built, every institution that humanity has ever founded, every tradition that humanity has ever maintained, while simultaneously performing the most complex engineering operation ever conceived, keeping a living ecosystem, a breeding population, and a technological civilization alive inside a metal container, flying through the emptiest environment in nature. The terrifying truth about the generation ship is not that the journey is long. Length is just a number. The terrifying truth is that 10,000 years is not a duration. It is a test of whether human beings can build something, anything, that remains stable, functional, and meaningful across a timescale that exceeds the lifespan of every civilization, every language, every religion, and every technology in human history. It is a test of whether the most adaptable, creative, destructive, and unpredictable species ever to evolve on Earth can also be the most disciplined, the most consistent, and the most faithful to a purpose across a span of time that makes the entire recorded past look brief. The ship's greatest enemy is not the vacuum outside the hull. It is not the radiation sleeting through the shielding. It is not the slow grinding of metal against metal as bearings wear and seals degrade. The ship's greatest enemy is time itself, not dramatic time, not the sudden catastrophe of an asteroid impact or a reactor explosion. Quiet time, the slow, patient, relentless accumulation of tiny changes in machines, in bodies, in minds, in cultures, in languages, in purposes, each one negligible in isolation, each one part of a drift so gradual that no single generation perceives it, but whose cumulative effect across 10 millennia is transformation so total that the thing that arrives bears only the faintest resemblance to the thing that departed. Could a generation ship keep humans alive for 10,000 years? Perhaps. If the vessel were large enough, if the population were carefully managed, if the ecology were robust enough, if the manufacturing infrastructure were comprehensive enough, if the educational system never faltered, if the governance never collapsed, if the knowledge were never lost, if the purpose were never abandoned, if 400 consecutive generations, each inheriting a sealed world they did not build and a mission they did not choose, each maintained the machinery, preserved the knowledge, managed the genetics, controlled the diseases, resolved the conflicts, educated the children, and passed the entire fragile enterprise forward to the next generation with sufficient fidelity that nothing essential was lost. Perhaps, but the answer is not really yes or no. The answer is that asking whether a generation ship could keep humans alive for 10,000 years is asking the wrong question. The right question is whether human beings could keep a generation ship alive for 10,000 years, because the ship is not the hard part. The ship is metal and ceramic and polymer and fuel. It can be designed, built, launched, and pointed at a star. The hard part is the creature inside the ship. The creature that forgets, that fights, that breeds unpredictably, that reinvents its own identity every few centuries, that abandons old gods and creates new ones, that loses interest in things its grandparents considered sacred, that breaks every institution it builds, and that has never, in its entire history on Earth, managed to keep any single project running for 10,000 uninterrupted years. The generation ship is not a ship, it is a mirror, and what it reflects is the most uncomfortable question humanity can ask itself. Not whether we can cross the distance between the stars, but whether we can survive ourselves, sealed inside a machine, with no room to run, no place to hide, no second chance, and no one coming to help, for longer than we have ever managed to survive anything. The people who launch the ship will not see the answer. The people who arrive, if anyone arrives, will not remember the question. Somewhere between departure and destination, across 400 generations of living, dying, forgetting and trying, the answer will be written. Not in any language the founders would recognize, not in any document they could read, but in the fact that someone, something, shaped by the journey into a form no one predicted, opens a door and steps out under an alien sun, or in the silence that means no one did.